you can read this. So fin tube heat exchangers can withstand high pressure on the tube side, and usually they're less compact than plate fin heat exchangers. And then there is the surface area density quantity, which we call the beta. So that's surface area divided by volume. So that is about 3,300 meters squared per meter cube. Now on the gas side, we have fins, and we want some amount of surface area so we get that much surface area by including adequate number of fins. So proper fin density and fin geometry. Then the fin densities for these plate fins, they vary from 250 to 800 fins per meter. And fin thicknesses vary between 0.08 to 0.25 millimeter, and fin flow lengths vary from 25 to 250 millimeter. Anyway, so we understand broadly how to proceed because we looked at shell and tube heat exchanger. So here, first we have to understand and quantify the geometry, because if you don't have adequate nomenclature for the geometry, various things like fins, tubes, etc., then you will not be able to have expressions for areas. Okay. Now, you can see a few things if you observe this fin tube heat exchanger. So this is inside an enclosure, and these are circular tubes, as you can see from here, and the fins are also circular. Okay, so when we talked about heat sinks, we looked at fins, but those fins are rectangular fins. Why did we study only rectangular fins? Because it's kind of easier. This circular geometry is the same approach, but the geometry is a little bit more difficult to deal with. So that time also I mentioned that, okay, there are circular fins also, which we are not studying, but you can understand those based on your experience from rectangular fins. Now let's get the number of tubes, the number of fins, etc. Okay, and then get expressions for areas. Why do you need areas? Because based on areas you have heat transfer. Based on areas you also have the hydraulic diameter, and then the hydraulic diameter helps you calculate the Reynolds number. From Reynolds number you get the Nusselt number, and from Nusselt number you get heat transfer coefficients, etc., etc. So the usual approach. Now, here what I will do is I will ask you to think about these expressions. So this is one, this is the second one, this is the third one, this is the fourth one. Okay, so let this be on the screen, let this figure be on the screen, and you tell me whether these appear okay or not. It will take you 2 or 3 minutes to visualize this, but tell me whether these are okay or not. Number of tubes in the first row is L3 over PT. Okay, so that's the first statement. Now, this is the flow direction, right? This is, you can say this is the flow of gas, and flow of liquid will be through the tubes, right? So when we talk about the flow of gas, then we have these tubes which are perpendicular to the flow direction of the gas. Okay, so is it okay to write L3 over PT? PT is the pitch. Okay. Study the figure and tell me whether L3 over PT is okay. Okay. How many of you think it's okay? Vedang, is it okay L3 over PT? This is not fluid mechanics, this is just some geometry. It's like a little puzzle. How many of you think it's not okay? L3 over PT. All right. So we're talking about the number of tubes in the first row. Okay, which is the first row? The leftmost. So now there are tubes which look like this. Okay. This is showing 3, but this dots indicate that there are few more in between, right? Now, so what is this distance? PT. Okay. So if you have 5 tubes in the first row, okay, actually it will be more than this typically. But if you have 5 like this, then this distance is 1, 2, 3, 4, 4 PT, right? Which means that if the number of tubes is n, right? This is n minus 1 into PT, this length, right? But there is additional length also, above and below, right? What are those? Those are this PT by 2 and this PT by 2. Why does it have to be PT by 2? I mean, it's just something that he has taken. If it is slightly more than that and less than that, it might not matter much, but in this arrangement, it's PT by 2. So total this thing, including this much here, little thing here and little thing here, is n minus 1 PT plus PT. So this is n times PT. This is the total length, right? And that total length, we have a name for that. What are we calling this? L3. Okay. So this is L3. So that means n equal to L3 over PT. That's how it has been done. How to remember which one is L1, which one is L2, etc. You just remember that for tube flow, this distance is L1. Okay. Keep this picture in your mind and have in this picture the flow direction, the flow of the liquid will flow through the tube, and liquid will flow through the tube. So this distance is L1, right? This is L1 and the vertical is L3 and this is L2. So L1, L2, L3. This is how it goes. Start from the back, and for the liquid flow, the liquid length, the tube length is L1. So you go L1, L2, L3, okay, in that sequence. So the height becomes L3. Right, so this is the number of tubes in the first row. What about the number of tubes in the second row? L3 by PT minus 1 is okay. Second row is staggered, okay, because we are essentially thinking of a triangular arrangement. So L3 by PT minus 1 will be okay. You are convinced about this one, L3 by PT? This one is okay because I worked out all steps. So hopefully you can work out the second row. So it should be L3 by PT minus 1. Second row will have less, right? Okay. So check this out yourself. I'm not doing all steps. Fine. So this is L3 by PT minus 1. Now, number of rows with the same pattern as the first row. So how do I do? This is one row. This is the first row. So the third row will have the same pattern as the first row. So the number of such rows, which are like the first row, that's this. Can you check this one? Right. So this is L2 by 2 PC. L2 by 2 PC plus half. This is the number of rows that are similar to first row. Okay, I'm asking you whether this is all right or not. So to understand this, look at this figure which I have drawn myself. This is not in the book, just to make it easier for you. Another figure. So this is the first row, this is the third row. This is the second row, which is a bit offset. Correct? So this distance is how much? It's 2 PC. So if this is 2 PC, then will we get this? We'll have PC by 2 on this side, we'll have PC by 2 on the right hand side. Okay, fine. I think we cannot derive all of these in detail, but I have to ask you to check these at home, right? I gave you the idea. So that's the number of rows similar to the first row, and the number of rows similar to the second row is this much. This also, please check. Okay. So this is L2 by PC, L2 by 2 PC plus half, and the other one is L2 by 2 PC minus half. Okay, last expression. So we got information on the number of tubes and the number of rows. Number of tubes in the first row, number of tubes in the second row, and the number of rows. Similar to first and similar to second. Okay. What's the point doing all this? This gives you the total number of tubes. Okay. This should be all right. What's L3 by PT? Number of tubes in the first row. And this one? Number of tubes which are similar to the first row, including the first row. Right? This is number of tubes in the second row. And this is number of rows which are of the same pattern as the second row. Okay, so this should be all right. Then the primary surface area becomes this. So you have that box with L1, L2, L3. Okay, so flow going like this, right? So L1, L2, L3. You can visualize this. All right. Now tell me whether this is reasonable or not. All right, one by one. What is pi DOL1? Pi DO multiplied by L1 is an outer surface area of a tube, right? Okay, that multiplied by NT will give you the outer surface area of all tubes, right? But we have to subtract this from pi DO L1. What is that for? That term where my cursor is. This is due to the fins, right? So look at this part of the figure. So there is a delta. Delta is the fin thickness. So these are the tubes. I am looking at the tubes from this side. So I'll see tubes and I also see the fins, right? I'll see individual fin thickness. So this is the fin thickness. And NF is the number of fins per unit length. So if you do NF times L1, then you will get the number of fins on a particular tube. NF times L1 is the number of tubes, number of fins on a particular tube, correct? And we have the thickness and then we multiply it by NT to take care of all tubes. Tell me what this is. Second term. What's L2, L3? It's that surface area of the faces, right? So the flow going like this, the flow apart from the tubes and the fins, the flow is also going to see the inside surfaces of this box, correct? And that inside surface is L2, L3, correct? If you are not clear, then let me tell you this, that I am trying to talk about, you see this area, as well as this area, inside surfaces. So those will be L2, L3. Isn't it? What happened, Pushkar? Not sure? Huh? Cursor is not there. I removed because I'm drawing, no? So that's why. Okay, so yeah. So this one, I just drew the arrows. If I have the pointer, then I cannot draw. So I go to pen, yeah, pen or pencil, whatever you call it. Right, so this one. So L2, L3. But that L2, from that L2, L3, we also have to subtract pi d naught squared by 4 multiplied by nt, right? Because those are due to these tubes going into the walls, right? And why is this 2? Because there are two surfaces, two inside surfaces of the box. So at these inside surfaces also there is some heat transfer takes place because the gas will see the inside surfaces of the box also. Okay. Right. And then this is the fin area. Fin area is, what's this? Try to interpret this one. This one. This is the annular surface of the fin. So if you look at the fin, okay, so this is DO, and this is DE. So this shaded area will be pi d square minus DO square divided by 4. But you have to multiply it by 2 because for each fin there are two sides, right? Okay, and what about this pi d delta? So that's because of the rim of the fin, right? That is because of this thickness of the fin. Okay, so you have to interpret all this. What I recommend is that you can keep the figure in front of you. Don't look at the expressions, isn't it? Very easy to do that. You open the book, then you cut this figure and then paste it on a Word file, and then just keep the Word file in front of you, and in your copy just write these expressions. Then go back to the book and check whether these expressions are correct or not. Okay. So that's AF, and the total heat transfer area is A primary plus A fins. Okay, but there is some other area also. So this area is free flow area. We like to calculate a free flow area also. So what we just now calculated is a primary area plus a fin area. Okay. So where is that primary area? The last thing that we did, this primary area is actually at the surface of the tube, at the surface of the fin, those things. Primary area plus fin area is basically what these things are giving, correct? But we are also interested in this area. What is this area? So the flow, so these are the tubes, right? Perpendicular to the tubes, you have the gas flowing, right? So if you look at this figure, gas is flowing like this, correct? So the gas will see that shaded area where my cursor is. So you need an estimate of that also, because that will help you calculate a hydraulic diameter. So just as you have flow in a tube, you are interested in the inside area, you're interested in the outside area, but you're also interested in the cross-sectional area, right? Because the flow goes through that, correct? So the open area is also important. What we have been talking about was not the open area, it was not the free area, right? It was only at the surface of the tube and at the surface of the fins. But this is an open area thing through which the flow goes. We need to have an estimate of that also. Now, that estimate is given like this. So that is based on, So these tubes, here you can see only two tubes. But behind these two tubes, so this tube is shown here, this tube is shown here, but as the flow moves in this direction, backside also there are tubes, correct? So if this is the first row, then this will be a tube belonging to the second row. Now the open area can be estimated like this. So this is the free flow area. So this minimum free flow area we call it. So this area is given by this. So is this okay? So we are calling it AC. AC is basically that shaded area. Okay. See, we almost spent half an hour just discussing the geometry, so I cannot afford much more time than this. Most of it you will have to check at home, right? So this is PT, and this is D naught. This is D naught by 2. This is also D naught by 2. So PT minus D naught multiplied by a perpendicular area perpendicular to this screen is the dimension L1, right? So we have PT minus D naught multiplied by L1. Okay? And then from that we subtract the contribution due to fins. Right? We are talking about which area again? So we are talking about this free area between the tube rows. All right, so this is what we are going to get. Details you have to do yourself. Now we have that area AC. The last expression was AC. So based on AC, we can calculate a hydraulic diameter. This hydraulic diameter, you know, it's like written 4A over P, correct? P is the perimeter. So here we are not using P directly, but instead of P, we are using the total area divided by L2. So 4AC is like, 4A over P thing. So this is 4AC is for that. And there is, instead of P, we are using AT over L2. AT over L2. Why L2? Because we want a perimeter, a wetted perimeter. So that will depend on this sort of area, which is AT, including the tubes and the fins, divided by this. What is this dimension? L2. So we are constructing something like a perimeter by calculating AT over L2. So this here we don't use L1. L1 is this dimension. Okay. But when it comes to the wetted perimeter sort of thing, you will have to use L2 because the flow goes like this. It keeps seeing these rows of tubes. Okay, so that's the hydraulic diameter. And based on the hydraulic diameter, you can also calculate the Reynolds number. Reynolds number is rho v dH over mu. And here you can write this rho v as a mass velocity. Rho v is a mass velocity. What's the unit of rho v? Rho is kg per meter cubed and v is meter per second. So kg per meter squared second, isn't it? So that's like a mass velocity. Professor Lee is calling it like a mass velocity. It's written it with a g, but it's basically the same thing. Like, so that the Reynolds number is just written in terms of g and dh. Okay. So this is one thing that we remember. Then the fin pitch is 1 over NF. NF is, what is NF? Number of fins per unit length. Okay, number of fins per unit length. So PF will be a pitch because it's length divided by a number, that sort of thing. So that will give you a pitch. Right. Okay. Good. Now we are moving towards correlation. So we got all areas, and based on areas, we got also a Reynolds number. Okay. And we now want to go to these correlations. So for correlations, sometimes we use a Stanton number. Stanton number you must have seen in undergraduate, right? Stanton number is Nusselt divided by Reynolds Prandtl. And it is also equal to H divided by GCP. So H divided by rho VCP. That's Stanton number. So Stanton number is another form in which you can bring in the heat transfer coefficient. Nusselt number has heat transfer coefficient, but sometimes it's more convenient to bring in a Stanton number. Okay. Because there's a Colburn factor, which is J. So J is Stanton multiplied by Prandtl to the power 2 by 3. So that's what this looks like. This part is Stanton. So we'll leave this heat transfer part here and then go to also friction factor. So if you have a circular finned tube geometry, then the Colburn factor has an expression like this. Now we are just blindly going into some correlations because we can't actually discuss correlations. So just pick up those correlations and use. And you know everything here, like what is PF? PF is 1 over NF. We just saw a few minutes back, right? And you have this 0.134, etc. Those we pick up from some literature. And this is J factor. And we also have friction factor. Friction factor is written as F as RB. So this RB is because of RB. What are R and B? R and B are because of a couple of people who did this work about 60 years back in 1966, old paper. So this is by Robinson and Briggs. So the advantage of writing is as FRB is that, okay, you remember that, okay, it's the Robinson and Briggs correlation. So these are odd things, odd numbers like this, but okay, we'll have to use this. This is a plot where the J factor and the friction factor are both plotted as a function of Reynolds number. So you have these lines which are, the solid lines are from the correlations. So this is a correlation for the friction factor, this line given by Robinson and Briggs, that's why we wrote FRB. But for J also, there is a correlation, which is this one, and that's plotted with this dashed line. What are the data? Data are from experiments, obviously. So these experiments were done by Case and London. So there are books by, there's a book by Case and London, I think. So, not convective heat transfer, there is a book on heat exchanger also. On convective heat transfer, there is a book by Case, but London's name is not there. All right. Now we don't try to remember these correlations, but we should know that, okay, around this page of the book, around in this chapter, these correlations are there. So the other thing that you can do is also you can prepare like a sheet with these correlations. So let's say for shell and tube heat exchanger, you write a sheet. Actually, for shell and tube heat exchanger, there's a long table which I had shown in the previous class, which has all these relations. So you can take a print of that maybe, and for this one you can. I don't remember whether for this one there is a table, but otherwise you can prepare these sheets like this is for friction factor, this is for heat transfer coefficient. Okay, so we got this, but what about pressure drop? Pressure drop is important. Why? Because we have seen in problems, you are typically asked to get some heat transfer, but you are also asked to contain the pressure drop, that the pressure drop should be less than this much. In the shell and tube heat exchanger problem that we had done, it was restricted to, the pressure drop was restricted to 10 kilopascal, both on the tube side and the shell side. Correct? So this is delta P. Delta P, this is an expression which I'm not explaining. If I get time, I'll talk about it in a separate class. Okay. So this pressure drop obviously has the friction factor. For friction factor, we have seen the correlation. There's a 1 over rho m which is used here, and 1 over rho m is half of 1 over rho I plus 1 over rho O. There is inlet and outlet. Okay, so this in this expression also you have a hydraulic diameter. We've already seen how to calculate the hydraulic diameter. Now, with all this, see, these things are actually not theory as such, but these are just, I'm just putting together some correlations and showing you that this is the stuff that we are going to use. Now let's take 2 minutes to read a problem. Just read this slowly, and as you read a problem, so in Thursday's class, we'll do some problem, and as in exams, you have to do some problems. So as you read the problem, keep writing. Okay, that, see, for example, this is m dot air is 124 kg per second, isn't it? So then T air outlet is 30 degrees Celsius. Things like that you should keep writing as you read the question paper. So this is the hot water flow rate, and this is entering at 92 degrees Celsius. The pressure loss allowed is 250 Pascal. On the air side and the water side, you are allowed 3 kilopascal. You have aluminum fins, copper tubes, thermal conductivities are known. You get a triangular pitch arrangement with equilateral triangle. So this is equilateral triangular pitch arrangement. Now there is a tube pitch, and there's also a fin pitch, obviously. And fin thickness is this much, and the diameters are these. Tube outlet diameter, tube inside diameter, and the diameter of the circular fin, right, which we were calling DE. Now you're asked to design the fin tube heat exchanger. What does it mean? It means that you get all the dimensions, adequate number of tubes, proper arrangement of fins, proper choice of fins, and ultimately you make sure that this much heat transfer takes place and pressure drop is contained, correct? Within that 250 Pascal on the air side and 3 kilopascal on the water side. Okay, you also have to calculate effectiveness. So this is broadly what it is, and this is a figure. So the book uses this sort of a figure for this kind of heat exchanger, and this you can see this is like you must have noticed by now that this is a cross flow heat exchanger, correct? So we have tubes like this, water going like this, air going like this, so obviously it's cross flow. Yeah, so this is a good idea. I mean, you can quickly draw this when solving a problem. It doesn't take you much time to draw this one. And then just write these numbers. And this will be a guide for you as you solve the problem. Okay, so this is again, I'm just repeating this figure. And this we call a unit cell. And this is a staggered finned tube arrangement. This is equilateral triangular pitch arrangement. Now, what are the temperatures that we know? We know these temperatures. So this is air coming at 5 degree. Air will go out at 30 degree. And water is coming in at 92 degree. We don't know at what temperature the water is going to go out. Okay, we still don't know that. But in order to do any kind of energy balance, you need properties, like you need Cp, right? Even if you want to do m dot Cp delta T, you need Cp. But to calculate Cp, you need some temperatures, isn't it? You do not know all temperatures. Even, I mean, you might think that, okay, let me do energy balance, get the 4th temperature. But even to do that energy balance, you need to have properties which need to be evaluated at proper temperatures, isn't it? But one temperature you do not know. So that temperature you have to assume. That's why I have underlined this word here. So the water outlet temperature he has assumed to be 76 degrees Celsius. So this is 76. So the water temperature is 84, air temperature is 17.5. And we can calculate rho 1, Cp1, Cp2, etc. Rho 2 he's bringing in later. And these are some of the properties already there in the problem statement. All right, nothing new here, and these are the design requirements. Ultimately, we want air at 30 degrees Celsius for whatever purpose. I don't know the purpose, but we want 30 degrees Celsius. And he has chosen some geometry. He has chosen a DI and DO. So he has chosen some tube, okay, some tube dimensions. Tubes are often chosen based on availability. That okay, this commercially I can buy, because obviously you will not make tubes, right? For a heat exchanger, you will not make tubes like custom made tubes. You will not do that. You'll try to manage with what is available in the market. You try to do this, and then he chooses something about fins. So this is the fin outside diameter, number of fins, and this is for the arrangement. PT, transverse tube pitch, etc. This is the fin thickness, and then we can get down to our calculations. So what he has done, he has chosen L1, L2, L3. And these are kind of like, it will seem odd to you that he has like 7.559 centimeter for L2. So he has got these numbers from somewhere. So I think what he must have done is that he chose some L1, L2, L3, did a design, then refined it. Maybe the first time he chose some L1, L2, L3, it didn't work out. He did a few iterations to get these numbers. Okay, that's my best guess. That can be part of this also, but let's say 7.559 centimeter. It's not exactly 3 inch either, isn't it? 3 inch is 2.54 multiplied by 3. You will not get this one. So what he's saying is that maybe it thought about it as an inch because he's in the US, but even if you think in inch, it will not be round numbers. Okay. So I suspect he has done some iterations and got this funny kind of number. Right. So after that, we already have this expression, which I described in quite a bit of detail. So you get NT as 105.588. He's again using some MathCAD sort of thing. So every time he writes a quantity, he writes functionality also. Okay, so functionality means that, okay, the number of tubes that you have, right, it will depend on L2 and L3 also. If you increase L2, if you increase L3, you will get more number of tubes for a particular tube arrangement, isn't it? You get more tubes. It's not, the number of tubes is not dependent on L1 because L1 is along the length of the tubes. Okay, whatever it is, don't bother too much about the MathCAD notation. So this is 105.588. So you can say 106, right? Number of tubes. And we have the primary surface area. Again, this is an expression which you need to check out yourself and be convinced that this is correct. And this gives you an AP. So AP is primary area, which is 34.692 meters squared. So that's quite a bit of area, right? 35, 30, let's say 30, so 6 meter by 6 meter is 36 square meter, isn't it? 6 meter is what? About 18, 19 feet, isn't it? 6 meter, 19 feet, more than 19 feet. 1 meter is how much in terms of feet? 3.28, correct. Like 19 feet multiplied by 19 feet, that area is actually contained in this primary area of these tubes. Just to get an idea of what we are doing. And then we calculate the fin area, and the fin area is 331 meters square. What was the other one? Other one was 35, let's say. And this is 331 meters square. To get an idea of what you are adding, imagine the increase in area that you were doing by adding fins, because such a large number of fins. Okay, and each fin gives you, like, if this is a fin, it gives you this side, it gives you the other side, right? Okay, so this, when you look at these numbers and try to imagine like how big these numbers are, then you get a feel for what we are doing. Obviously, we are making it, making the heat transfer much more effective by increasing this area. So the total heat transfer area, which we are calling A2, is AP plus AF, and AP plus AF is 366. All right. And yeah, what else? We also will calculate that AC. AC is that shaded area. I said this is the flow area basically. correct? You remember which one am I talking about when we say AC? AC is, you have these fins, you have these tubes between the tubes, right? It's that area. Shaded area. That what we were calling as this thing basically. Okay, I think we ought to stop. Now it's 11:53.